Hello and welcome back. Today we're going to solve the homework exercise for the law of large numbers. Let's get straight into it. So this is our exercise. Let's just quickly refresh what it was about. Test the law of large numbers for n random normally distributed numbers with a mean of 0 and standard deviation of 1. And that means create an R script that will count how many of these numbers fall between -1 and 1 and divide by the total quantity of n. You know that the expected value of your measurement is 68.2%. Check that the mean of the actually measured value is converging to the expected value as you rerun your script while increasing n. So that was the exercise, and let's get straight into it. Let's dig into the code. Okay, so here I've got RStudio and I've got a blank new script, and we're going to create this solution together. First thing we need is the rnorm function. As you remember, we used rnorm with the value of 1, right? So we ran rnorm like that, and it would generate us a new random variable from a normally distributed sample every single time, right? So now what we want is we want 100 of those variables. So to do that, we need to replace the 1 with 100. And what we'll get is a vector of 100 of those numbers. So you can see all of them here. So first one, second, and third, fourth, fifth, and then sixth one, and that's what this actually 6 represents here. 6, 7, 8, 9, 10, then 11, and so on. So here we have our 100 normally distributed variables. Great. So now we need to create a cycle through, or a loop through, all of these numbers. In order to do that, we need a for loop, right? So let's create a for loop. And as you remember, we need a for, then we say I in, and what did we used to say? We used to say 1 to 10 or something like that, right? So then we've got the curly brackets, right? So we used to create loops like that. And what was this? Well, we knew that this was a vector of 10 numbers. So in this case, we were cycling this index through these 10 numbers. What we want to do now is we want to replace that vector with the vector that we actually want to cycle through with the rnorm vector. So we want I to go through all of these numbers that we've created here, and bear in mind that every time we rerun this script, it'll be a different 100 numbers. So we want I to go through all of these numbers, and then we'll do something with I in there. So hopefully that makes sense so far. Let's start typing up the body of this for loop. So here we're going to say if, right? We want to check, does I fall between -1 and 1? So I'm going to type this up and then I'll explain it. So I is greater than -1 and I is less than 1, right? And then we'll have the body of our if statement. Now, the very interesting thing here is that, especially for those of you who come from a programming background, who've programmed even at least once in any other programming language, what you will notice is that here we're actually using the I letter itself rather than using the I letter as an index. So in another programming language, you would hypothetically write something like this: I is greater than 1 and I is less than greater than -1 is less than 1. And that's if you're cycling, is if you're using I as an index to go through an array. And let's say A was this, like all this of course is completely incorrect, but hypothetically, if this was your array, you would be running through it. But what we're doing here is very different. Even though we're creating a loop, I is not our index. Even though it's the letter I. What it's doing, this variable I, is it's actually taking the values of these normal variables, normally distributed random variables that we're generating. I is taking them one by one. So in the first iteration, I will be equal to this. I won't be equal to 1. It won't be equal to 2, 3, 4, 5. It's not an index. It will be actually taking the actual value. So I will be equal to 0.75 in the first iteration. In the second iteration, I will be equal to -1.26. Then it will be equal to 1.877 and so on. So every single iteration, I will be assuming one of these values that we have generated, so the next consecutive value. And so that's why we're actually operating with I. We want to check if the value itself is greater than -1 or less than 1. If it makes things easier for you, you might want, while you're learning this and getting used to this method, because it took me personally, it took me quite a while to get used to this. Like first I wrap my head around this, what's going on, why is I not an index, but then to get used to it. So you might want to change the letter I to say X or something like that. So that way you won't be tempted to think of I as an index. But we'll just keep it as I for now, just for consistency purposes. And what do we want to do now? That now we found out, yes, if this condition is true, I is indeed between -1 and 1. What do we want to do inside this if statement? What do we want to tell R to do? Well, what are we doing? We're counting the number of these, the quantity of these numbers that fall between -1 and 1, right? We want to know how many of them are there. So this one would fall in there. This one wouldn't. This one wouldn't. This one would fall in there. This one would fall in there. So we want to count them. How do we count them? Well, we've already done an exercise like this before. We need a counter variable. So we need a counter variable that starts with 0 before we even launch this loop. But then every time we find one of these variables that we're interested in, we got to increase the counter variable by 1, right? So we've got to say counter is whatever counter was before in the previous iteration plus 1. So in the first iteration, as soon as we find, so not in the first iteration, as soon as we find one of these variables, counter will be increased from 0, it'll be 0 plus 1, it'll become 1. Then the next iteration, or the next time we find another one of these variables, so here counter will be immediately increased from 0 to 1. Here counter, nothing will happen. This part of the for loop, the condition won't be true, so the body of the if statement won't be executed, so the counter won't change on this iteration. On this iteration, the counter won't change again, but on this iteration, the condition will be correct, so it will be true, so the body will be executed, and the counter will change from counter was 1, and now it'll become 1 plus 1, it'll become 2, and it'll be stored here in the memory, and then it will move, the studio R will move on to the next variable, and this time the condition is true again, so counter will become 2 plus 1 equals 3, it'll be stored in memory, and then R will move on to the next iteration. This time condition is not true, so counter will increase, and so on. So every time we find a variable, the counter will increase by 1. So every time we find a number that we are interested in, so every time this condition is met. Okay, so that's the main part of our loop. So what do we want next? We want to print out counter, right? We want to find out how many of them were there. So this is like the start. We've created the bulk of our program now already. So how about we just run it and see how it works, okay? So let's select all of that and command run, right? So here we have 68. Let's run that again. 68, 70, 63, 71, 65. So it's telling us how many of the numbers that we've generated out of the 100 numbers actually fall between -1 and 1, right? So we can keep running that, and every time we're going to see a new set of random normally distributed variables, and this number will change. Okay, so what does the exercise ask us for? Well, the exercise asks us to compare that percentage, the percentage of these numbers, to 68.2%, right? So let's just put a comment here so we remember. Compare to 68.2%, right? So here we've got a number, we want a percentage. So in order to get a percentage, we need to divide by 100, right? So, or that'll be the ratio, right? So in that case, we'll be comparing not to 68.2%, or let's just leave that, or 0.682, right? So we need to compare to that. So let's run that again, and now we have a ratio, right? So as you can see, it's kind of, there we go, there's a 0.68. But because the sample is quite small, sometimes you'll be off to the left, sometimes you'll be off to the right from what you're expecting. And that's exactly what the law of large numbers tells us. The sample is quite small, and so there's a higher likelihood that this number will be different. But as we increase the sample size, this should change. So how about now we, instead of 100, we put in 1,000. So let's change both of these. It's important to remember to change both of them because there's a total of 1,000 numbers, so we need to divide by 1,000, right? So now let's rerun that. So as you can see, now we are getting closer again to the 0.682. There we go. And finally, what we want is we want a variable to control this script, right? So that we don't have to change it twice every time. We want a variable n at the top to control this whole script. So in order to do that, we need just the variable n, and then we'll give it a value. So let's start with 1,000, and then we'll replace n here. We'll press n here, right? So now we don't have to change it every time twice. We only have to change it up at the top, and it's easier like that. So somebody who's using a script will know that this is the input. You can even say here hashtag input, and you can see how comments can be useful for people who are running your script, who are not you and who didn't create the script, but who are running your script. So they don't have to worry about all of this, right? They just have to worry about this bit. Okay, so there's our script with 1,000 variables or numbers. Now let's change it to 10,000 and see that if that improves how close we get to the expected value. As you can see now, it's 0.68 pretty much all the time, right? There's no more 0.71, no more 0.7 or 64, and so on. So, and now if I add a couple more zeros, so what does that give us? It's 100,000. No, that's a million already. So we're generating a million random normally distributed variables, right? So you can see the computer was thinking there for a second, and you can see now we're very close, right? It's always 0.68. 682 something, 683. So we're getting closer and closer. So if I add another zero, the computer will think for a bit longer. My poor little MacBook. Okay, so you can see it's taking some time because it needs time to generate these numbers, but more importantly, it needs time to run through all of them. And there we go. So 6.82. So as you can see, we're getting closer and closer. The more we have in our sample, the closer we get. And that's exactly what the law of large numbers tells us. So there we go. We have confirmed that the law of large numbers holds in this exercise. We have actually tested it and demonstrated that it works. Hope you found this exercise useful. Hope you enjoyed creating this code together with me. And I look forward to seeing you throughout this course. Until next time, happy coding. Hello and welcome back to the course on R programming. Let's go ahead and solve this challenge. These are the things that we are after. So let's go ahead and calculate them. So profit, what is profit going to be? Profit is, create a vector, profit is revenue minus expense. Run that, expenses, run that, and let's just check it now. There we go. So we've got our profit vector, and this is our first vectorized operation in this challenge. Awesome. All right, profit after tax for each month. So first we're going to calculate tax. Tax is going to be profit multiplied by 0.3, right? Run that, and let's have a look at tax. What we see here is that there is more than 2 decimal points, and in the challenge it specifically said that we should perform calculations at the precision of 1 cent. So we need to round this. So we're going to say round profit. But how do we use round? Yeah, how do we use this function? If I run this now, it did work, but what do I get? I get no decimal points at all, which is not correct. So how do I find out what to do with round? Well, let's find out more about this function, right? Round question mark, and here we have rounding numbers. So let's zoom in into this area over here and have a look. If I scroll down, I will see that there's my round function, and it's got x is the vector that I'm passing it, and then digits is an additional variable. By default, it's 0. So digits is an integer indicating the number of decimal places, round or significant. We don't need this bit, that's for a different function. Number of decimal places to be used. Negative values are allowed. See details. Okay, so that basically means how many decimal places we want to use, and we want to use 2. So let's put in 2. There are 2 ways. We can just say 2, or we can say digits equals 2. Both are identical because digits is the second variable, second argument of this function anyway. So let's go ahead and run that and check now. So there we go. We've got our precision as requested. Good. Now let's calculate profit after tax. By the way, in R you can simply put dots inside the names of your variables. It's totally fine, unlike other programming languages, and that makes it easier to separate words. You don't have to use capital letters. So we're going to say profit minus tax. By the way, if you look here, this is our tax values. You'll see that some of the months have negative tax, and that's totally fine. That's what was noted in the challenge. You can have negative tax. So profit after tax is profit minus tax. Let's check now. If I type in profit, you see it comes up for me already. So there we go. That's our profit after tax. All right, we've done that. What's next? Profit margin for each month equals to profit after tax divided by revenue. So let's go ahead and calculate that. Profit margin is profit after tax divided by revenue. Basically, it means how much of your revenue that you're making in this business is actually becoming the final profit. So some of the revenue is going into expenses, some of the revenue is going into tax, and so on. So how much does the business actually get to keep out of all the sales that it makes? So revenue is the same as sales divided by revenue, and we get profit margin. Let's have a look at it. Okay, so that's not exactly what we wanted. We wanted a percentage, right, with no decimal points. So let's go ahead and do that. So we'll say round by 2. So that will already get us closer, and now we have to multiply by 100 to get a percentage. And there we go. So that's our percentage. No percentage sign, and that's okay. As the challenge said, we don't really need a percentage sign. So as you can see, 12% profit margin, meaning that of every dollar that the business sold, so if it's a big shop, then if it sold goods for $1, then it gets to keep 12 cents after the expenses are paid and after tax. So tax and expenses in that first month in January, they ate up 88 cents for every dollar the business made. Then in February, they ate up 82 cents. So it's good to understand these things, like what are we actually calculating here. Profit margin in March was negative, meaning that for every dollar of sales that the business made, the business had to pay $1.30 in expenses, right? And if you look at the tax for that month, which was somewhere up here, it was actually negative. That's okay, and that's normal, because if your profit's negative, then, well, in Australia anyway, and so this is it might not be in all jurisdictions, but in Australia, if your profit's negative, then you get a deferred tax asset, meaning that next time when you pay tax, you will get to pay less tax. So that's a good thing. Anyway, so, but basically the expenses were very high in these months, and that's why the profit margin was negative. And basically means that, if the business wasn't operating, of course, okay, we're getting into too much finance here. If the business wasn't operating, then it would have still ongoing costs like rent and so on. So maybe it would have made even a higher loss. But for some businesses that don't have ongoing costs, this means that they should have probably just not worked in those months. Anyway, the business made up for it in the months following that. All right, so good months. Let's look for the good months. How do we find good months? Where the profit after tax was greater than the mean for the year, right? Than the mean profit after tax for the year. So first thing, we're going to need to find the mean profit after tax. So we're going to say mean. I'm not going to type in profit after tax. So I'm just going to say PAT. Mean PAT is going to be mean of the vector profit after tax. So we're taking a vector, which is profit after tax, and we're taking the average of all of these numbers using this function, a mean. And if we run that line, then we look up mean PAT, we'll see that that is our value. So we get one value in return. Okay, so that's our mean PAT. Now we need to check the good months. Good months is going to be a vector, as was stated in the challenge. Good months is months where profit after tax is greater than the mean for the year, which is mean PAT. We check that and have a look now. Good months. So now we have a vector of true, false, true, false. So first month was good. Then we had 4 negative months. So if we go to profit after tax, you'll see even though this month is positive, the mean for the year is this. So it's $1,700. In the second month, in February, it was only $1,300. So therefore, it makes sense that this was not a good month. Even though it was positive, it was a bad month. It was below average. And our accounting friends said that that's how they're going to determine good and bad months. So we got 4 bad months here, then a streak of 4 good months, then we got 2 more bad months. Looks like these guys are doing well in summer. So January, February, March, April, May, and then June, July, August. See, these are kind of insights you can derive already while you're even doing such a basic challenge. So these guys, this company seems to be doing better in summer. So maybe you can tell that to your accounting friends, hey, by the way, I did what you asked me. Plus, I noticed that they have a streak of good months during summer. And what is this? December, January. Wow. Okay, what does that tell us? So Summer is summer holidays at school, right? And August, June, what was it? January, February, March, April, May, June, July, August, September, and people go back to school here. And then December, January, right? What does that mean? Well, again, holidays. So maybe this business is holiday oriented and they are doing better in the holidays. Maybe, like if you were analyzing the business and trying to give them some advice, maybe you'd say, hey, you should work in the holidays period. You're better off working in the holidays period. Okay, so that's just how I think when I perform things like this, when I work with data. Because working with data is interesting, right? It tells you things that you otherwise wouldn't see. All right, so good months, profit after tax, we've done the good months. How do we get the bad months now? So bad months are the opposite of good months. So let's just say good months, and let's practice something we learned in the first section. Let's practice exclamation mark. Exclamation mark is the opposite, right? Gives you the opposite of a logical expression. We know that this is already a logical vector. If we take the opposite of the logical vector, we'll get an opposite logical vector. So let's type that in, bad months, and let's have a look at it. So if you compare the two, see true, and then it became false. False became true, false became true, false became true, false became true, true became false, true became false. So now you see the bad months. Bad months are here, and bad months are here. Okay. Makes sense. And now let's move on to the next one. Oh, that was the next one actually. So let's copy that, put it in here. Bad months. Okay, gonna make some space. Now the best month. As you remember in the challenge, we still want a vector. So we want just a vector of false, 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 and true just for the best month. How do we find the best month? Well, first we're going to need to compare to the maximum, right? Revenue. So we could do the same thing. We could create max PAT and put it in a variable, put the max value in a variable and then compare to it, or we can just do it on the fly. So let's practice that. We're going to say best month, profit after tax, and we're going to compare. So it has to equal, exactly equal. Remember, it has to be a double equal sign, equal to max profit after tax. So what we're doing here is similar to what we're doing here, right? So we're comparing R studio is going to, or R is going to compare each and every one of these values to this value. That's how it will work, right? Remember the whole notion of recycling vectors. So here we have a vector of 12 values, and here we have a vector of just one value. So, and then what R will do is we'll take this one vector, we'll put it, compare and put like recycle it 12 times. And so then this whole vector will have an identical length in length vector to be compared to. It's just, this is thinking of, now we were just thinking about accounting just now. Now we're thinking about programming, how programming works in the background. Well, that's how it works. So basically, you're not just comparing line by line, right? You're not comparing this value to this value, this value to this value, this value. Remember, we're working in vectorized operations. So what is actually going to happen is this vector, this resulting vector of length 1, which is over here, it needs to be compared to a vector of length 12. What's going to happen is this vector will be recycled until it has length 12, and then two vectors of length 12 will be compared, and then basically, so you'll have a vector, this vector being, so this vector of 12 values being compared to these 12 values. So basically this vector on the right is going to be created. It's going to look like this. Repeat. I'm just explaining here what's going on. It's good to know because it helps you think in terms of programming. So basically the profit after tax vector, which is over here, will be compared to this vector. And as a result, have we run this operation yet? We haven't run this operation. As a result, you'll get the best month vector, which is false, 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 true. December was the best month, right? So this will be compared to this, it'll be false. This one over here will be compared to this one, false. Is it equal? It's not equal. Is this equal? Not equal. Is this equal? Not equal. And so on until, let's power through it. Not equal, and then still not equal. Still not equal, this one to this one, and then it gets to this one and says, aha, equal, good. And that's how it gets this false, 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 true. Once again, it's good to know these things. It's good to think on the level that your programming language is thinking, because you will get along better that way. All right, so, and finally, the worst month. You can't just simply do the exclamation mark operator here because there's one worst month, not 11. So we're going to say, do this same thing, but instead of max, say min, and then say worst month. There we go. So let's check that out. There we go, false. Worst month was February, March. Worst month was March. All right, good. We've done everything we needed to. Now let's print them all out. Oh no, actually we still need one more thing. That's right, because if we print them out, so if we look at profit, not profit margin, if you look at profit after tax, for instance, it's got, it's just in dollars, but we were asked what we were asked. Let's go to the next slide. Results for dollar values need to be calculated with 1 cent precision. We did that, but need to be presented. So the final result needs to be presented in units of thousands with no decimal points. So let's do that now, right? So all of our dollar values, which we're going to include in the final result, which are just for consistency, we'll include revenue, expenses, profit, and profit after tax, right? So let's go ahead and fix them up. Units of thousands. All right, so revenue dot, let's say dot 1000, just so we remember what it is a revenue. And this is us practicing the round operation. So if we run that, and then we just look at revenue 1000, oops, you'll see that it's not rounded properly, right? We want units of thousands, but with no decimal points. So we want round, and then not 2, because if we do 2, we'll have 2 decimal points. We want just 0, right? Or because 0 is the default value, we can just not even specify it. Remember, for round, here we saw that if we zoom in here, we'll see that the default value of digits is actually 0, so you don't have to specify it. If you want to get rid of the decimal point, just do round. All right, so that's revenue 1000. Now let's do the same thing for expenses dot 1000 is around, whoops, expenses divided by 1000. And then what are we going to do? Profit dot 1000. Actually, I'm going to just copy this. Okay, so this one's going to be profit and profit over here. There should be some music playing in the background while I do this. But that's the reality of life, right? Profit. Sometimes in programming, you got to spend some time to create something that is worthwhile. Okay, so we've done all of these, so we haven't run this and this. And voila, we're done. Let's present the final result output, because we're not going to export. We haven't learned to export stuff and things like that. What we're going to do is we're just going to run this and as if we're presenting to the client on our computer. So we're going to say there's a revenue that you gave us, is expenses, but presented in units of thousands. There's our profit. There's our profit after tax. As you can see, it's kind of like smaller, but the negative one is greater because tax can be negative. There's a profit margin, and there's our good months, bad months, best month, worst month. Okay, so that's that. That's the challenge done. Now I wanted to show you a bonus, a little bonus for sticking around this long, I guess, for persevering to the end of this challenge. So what I want to show you is something that we're going to study in the next section of the course, and it's called matrices, right? So we're going to create a matrix. Now, don't be afraid. It's not like in the movie. I'm not going to offer you any life choices. We're just going to create a matrix. So we're going to say, just follow this code. And then in the next section, this is like a preview of the next section. You'll find out what it all means. So rbind, so row bind, and then we'll just take all of this stuff and put it in here. And now we just have to put commas. So if I run this, I've created a matrix, and let's print it out now and have a look at what it looks like. No, there it is. Aha. Okay, so not enough space. Let me fix that problem. I'm going to rerun this. There we go. So you can see that what we presented previously here is a bit like kind of, you know, some of it is okay, but then it goes out of line and it's hard to follow along. If you look at this, it looks beautiful, right? And notice that all the true falses have been changed to ones and zeros, which makes sense, right? And it's easy to read still. 1 is true, 0 is false. And everything is nicely aligned. You've got the first, second, you've got the months numbered out. By the way, you can totally change this. I'll show you how in the next section how to change the headers here and the headers here. So it looks much better like this, looks much better in Matrix. And now this is something much more pleasurable to look at, and you can present this to your friends in auditing who asked you to help them out, and they'll be pretty impressed. They'll be like, oh wow, that's pretty cool. And there you go. Hope you're excited about matrices. We will talk about them in the next part of the course. But most importantly, I'm pretty happy we got to practice these vectorized operations and also combine financial statement analysis with programming. That's pretty cool. I think that's pretty cool. In the previous section, it was statistics and programming. Now it's financial statement analysis and programming. What's next, right? What's coming up next? Anyway, happy that you stuck around. Thanks for your attention, and I look forward to seeing you on the next tutorial. Until then, happy coding. Hello and welcome back to the course on our programming. So let's go ahead and solve this homework exercise. Alright, so here I've got the file open, the section 4 homework data.r file that comes in a zip file. And this is what it looks like inside. So here we scroll down, you'll see we've got the seasons vector, the players vector. Then we've got the vectors for free throws, then no matrix, which we'll have to create it ourselves. And then there's the free throw attempts, also the vectors, and we're going to have to create the matrix. As you can see, my environment right now is empty, and we're going to proceed with these matrices to start off with. Okay, so I'm going to run this line by line. So first we're going to run this line. There we go, that's the seasons vector, then the players vector. And now if we run all of these, let's run them all together. Okay, so now we have all of these vectors that we want to put in a matrix, right? So there they are. All of these 10 vectors. How do we put them in a matrix? Well, let's start coding this up. We're going to create a matrix and we'll call it free throws. And we're going to use which function? That's correct. We're going to use the rbind function. And now we're just going to list these vectors one by one, comma after the comma. All right, there we go. So I've put all 10 vectors into the rbind. Let's just check that there is indeed 10. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Perfect. Okay, so that's going to create our matrix. If we run this line, now we've got the free throws matrix. It's ready. Next, what we're going to do is, as in the previous examples in the section, we don't actually need these vectors anymore. We have the matrix. So just to clear up the working space, we're going to practice removing these vectors. So we'll just take all of these, put them in the rm function. So if I run this line now, I've got rid of the vectors. That's good. Now let's have a look at free throws. Okay, so if I run that, you can see that there is our matrix. As you can see, it doesn't have the correct names. It's got the names of the vectors here on the left instead of the names that we want to see, and that would be these names of the players. And also it doesn't have any column names. So let's go ahead and fix that up. We're going to say, let's start with the columns. So we'll say column names free throws, right? So if I run that, I'll just get null because no call names. But now we're just going to use this vector that we have, seasons. So let's put that in there. I run that, and now a similar thing. We'll say row names for free throws is going to be players. Run that, and now let's have a look at the matrix free throws. There you go. It looks beautiful, right? So we've prepared this matrix. It looks fantastic. Okay, so I'm just going to remove this line because then for somebody who comes along and just runs all of the code, we don't want that check to pop up, but the rest of the lines are valid. Now, if you want to go ahead and do this part yourself, feel free to do so. What I'm going to do is I'm just going to copy all of this, and I'm gonna use a bit of a shortcut. So let's just copy that in here. And now what we want to do is we want to replace wherever it says FT by pressing Ctrl F. I'm going to replace that with FTA, and I'm just going to find them one by one so I don't replace other ones somewhere else in the code. There we go, and I don't need to replace those anymore. Okay, so that's fixed. Here I just need to change this free throw attempts, and that's also over here. So let's do that. All right, beautiful. So let's check this out. So if I run this line, okay, I've got a problem somewhere here. Kobe Bryant FTA. Oh, that's right, because I haven't run this code. So let's go ahead and run these vectors first. Okay, now if I run this line, there we go, that's the matrix, that's removing the vectors, that's fixing up the column names, row names, and now we can just go ahead and check this matrix. There we go, that's our free throw attempt. Beautiful. So we can remove that, we can save this file. We don't need the search functionality anymore. That's wonderful. So that's prepared. What do we need to do now? So that's just our data preparation phase. What do we need to actually find? So here's the challenge for this section. We need to find these three things, or build these three diagrams. We need free throw attempts per game, accuracy of free throws, and player playing style 2 versus 3-point preference excluding free throws. All right, so let's get straight to it. We're going to need a new file, right? So let's create a new file. And here we're going to, first of all, we're going to go into our previous file where the function is for plotting, and we'll just take it and copy it so that we have it in here as well. And then we're going to run this function, or create this object actually. There we go, that's a function. It's been created. And now we can go ahead and use it, right? So let's start by plotting the free throws. It's not required from us, but just to see what it looks like, because it is a new data set that we've just incorporated into our analysis. So there we go. Let's just rerun that so the legend looks good. All right, so that's the free throws just by themselves. And what we're checking here is for any anomalies, like does something look odd? Maybe there's something wrong with the vectors, or maybe we didn't create the matrix properly, but it looks okay. So let's do the same thing for attempts. That's the free throw attempts. All right, great. So now we can proceed to the analysis. So first thing, we're checking free throw attempts per game, right? So in order to obviously visualize this, we're actually going to need the games matrix. As you can see, we don't actually have the games matrix here because it was in the original dataset. So I'm going to go back to the original dataset that we used in this whole section, and I'm just going to rerun the whole thing, run it, and that will give us those extra matrices that were in the original challenge for the whole section. So there's the games matrix, and now we can go ahead and use it in our visualization. So I'm going to say my plot and free throw attempts divided by games. So if I run just this inside part, what I'll get is a matrix. Let's make some space here. So what I'll get is a matrix that actually has the information on how many attempts per game each player had, right? So that's a matrix separation. I'm dividing every element of this matrix by every element of this matrix. And that's something we talked about quite a lot in this course, in this section of the course. And now what I'm going to do is I'm just going to plot this whole thing by running this line all together. So if I run that line of code, this is the result that we're after. This is free throw attempts per game. And let's have a look at this chart. So what can we see here? So we can see that players average about somewhere anywhere between 2 to 12 free throw attempts per game. And so some players are quite up there, well, were up there. Now in the most recent season, everybody's kind of under 8 free throw attempts. And what else can we see here? Well, let's have a look at Chris Paul. So this will be an interesting one. So if you look at Chris Paul over here, you can see that his free throw attempts are quite low. So currently he's sitting about between 4 and 6 free throw attempts per game. And let's just remember that because it'll be interesting to kind of revert back to it when we create the next visualization. So let's proceed to the second one. So number 2 is free throw accuracy, right? And how do we get accuracy? Well, we need to take, well, obviously my plot, and here we want to take free throws. That's the number of successful free throws and therefore the number of points. Well, in this case, we're just looking at the successes. We're interested in how many successful free throws they had, and divide that by free throw attempts, right? So if I run this line, what you'll see is a new chart, and this is their actual accuracy. And you can tell that it is indeed an accuracy because it is between 0 and 1, or actually 0.5 and 1. So obviously it can never go over 1. And why did we look at Chris Paul last time? Well, look at Chris Paul here. So this red triangle, you can see that his accuracy is actually one of the highest, right? So his accuracy is over 0.85, and it's actually, in the last season, it was the highest accuracy, about 0.9, higher than all other players. And I personally found it quite surprising that he has the highest accuracy when it comes to free throws, but he gets the lowest number of free throw attempts per game. And that is a finding that you'd probably expect in a movie like Moneyball, right? So that maybe I'm sure the coach of his team and the whole team themselves, they have a strategy, but maybe this is something that they overlooked, and maybe you could communicate it to them and say, hey guys, actually Chris Paul has the highest accuracy, but he's not getting as many free throw attempts. So if you look here per game, so he's not getting as many free throw attempts per game. And maybe if you give him more opportunities to do free throws, maybe then he will actually score more points. He'll have more converted free throw attempts. That's just a hypothesis, and basketball fans out there can comment on that further, but that was just an interesting finding. Another thing you'll see from this chart is that Dwight Howard over here has a very, very low accuracy when it comes to free throws, right? And that is very surprising because that name rings a bell, right? Don't you think so? Let's look at something over here. Let's look at field goal accuracy. Field goals divided by field goal attempts, right? Remember we had this plot in our data. So here we've got Dwight Howard, and he's got the highest accuracy when it comes to field goals. But in free throws, he's got the lowest accuracy. And I found that very confusing. I did not understand what's going on there at first. And this is something the data is telling us, but at the moment we don't have enough information to understand what's going on. So let's investigate that further, and this is where this part 3, player style, will come in handy. So let's look at that. Part 3, player style. So let's type that up. Player style patterns excluding free throws, right? So this is that chart that we want to create, fix up basically the points. So we had points in our data set. We want to subtract free throws because every successful free throw is 1 point. So therefore it makes sense. We don't need to multiply by any coefficient here, just minus free throws. So basically this gives us all of the points that a player earned in that specific season from just field goals, not from free throws. And then we divide by field goals, right? So we want to see how many successful field goals that player had. So if we run this, we'll get that matrix, and this matrix represents the playing style. So it's hard to see from the matrix. Let's plot this visualization, and that will help us see everything much better. So there we go. From this visualization, we can see right away that we are looking at what type of goals the players are aiming at. So we can confirm that our visualization is correct, or our calculation is correct, because now the visualization is between 2 and 3. It's actually between 2 and 235. That makes sense because in basketball, if you're scoring a field goal, which is not a free throw, you can only either get a 2-pointer or a 3-pointer. You can't get anything else. So obviously the average will be between 2 and 3, right? And so here you can see how the playing styles have changed over the years. For instance, a very radical example is Joe Johnson, right? So he started 10 years ago with an average in that season. His average was 2.20 or 2.2 points per field goal. Then it went up, so he started aiming for, or started scoring more 3-pointers on average. Then it went down over the next 4 years, and now it's gone drastically up. So it's gone down in the past year, but a year ago it was 2.35, right? So he was scoring way more 3-pointers than he was 5 years ago. And that just shows that his playing style has changed. Maybe it has something to do with his training, maybe it has something to do with his coach, maybe it has something to do with his position on the field. Lots of different factors can influence that, but it's very interesting to observe how playing style has changed. Or for instance, Chris Bosh over here, he always was mostly aiming for 2-pointers, just a few 3-pointers, but recently in the past 2 or 3 years, he's started to get more 3-pointers, right? So, and you can also see kind of interesting trends that are similar. So for instance, this red line went up, this blue line went up, this black line went up, the green line went up. So it looks like in the recent years, most players are aiming for more 3-pointers, but then there was this like drop off over here. So a very interesting kind of patterns. And if you're a fan of one of these players, you can probably tell what was going on. This is the most interesting part, where you combine insights from your data with actual domain knowledge and your understanding of the game itself. So that would be the most interesting part, I think. Or even if you're not a fan, you can go ahead and just research what was going on with either of these players if you're interested to find out more insights. So that's number one. But now let's go back to that conundrum, or that question we had about who was it? About Dwight Howard, right? So Dwight Howard is very accurate when it comes to field goals. He is not accurate. He's the least accurate player when it comes to free throws. What is going on there? Well, this chart, if you look at this chart, you will find the answer. I'll probably give you a second to think about that for a couple of seconds. And what I found is that you can see that Dwight Howard is actually very, very low over here, consistently scoring only 2-pointers. Maybe occasionally he's got a few 3-pointers in, but generally he's only aiming for 2-pointers, right? And that explains it all. That means that when it comes to field goals, and we're talking about field goals here, he is always scoring 2-pointers. And 2-pointer means that you can be close to the net, or in fact, you might be even intact with the net. You might be so close that you're dunking the ball into the hoop, or you're just very close that you can basically just drop it into the net. And even not knowing anything about Dwight Howard or his playing style, I can already tell from the data that most likely he puts the ball in when he's very close to the net, because that way it explains why his accuracy, let's look at it again, in field goals is very high, right? If you're so close to the net, it's hard not to put it in. And then he doesn't take shots from far, and they don't drop his accuracy as opposed to other players. But when it comes to free throws, he's not that good, right? Because you can't be close to the net. You have to be 15 feet away from the net to throw in a free throw. And apparently his throwing accuracy is not that good. And that explains all of this data. And when I found these insights, it was very interesting and actually satisfying to finally find the answer and see how all of this comes together, that you need to look at these 3 tables or 3 visualizations to understand what exactly is going on. So there we go. That's our 3 insights as requested by the challenge. I'm sure you had lots of fun creating these visualizations and investigating the basketball trends. And moreover, now you have 2 additional tables and you've got all of this data, so feel free to play around and see what other insights you can find. As you can see, it's very interesting what you can tell from the data, even not knowing anything about the game. And I look forward to seeing you next time. Until then, happy coding.